Hi, so in today's video we will be looking at buffers and how they work, and we'll also be looking at the Henderson Hasselbalch equation. So our first question is, what is a buffer solution? Well, there's a few things we need to know about a buffer solution. So a buffer solution is simply a solution that resists pH change. So this means that when we add a strong acid or a strong base to our buffer, the pH is not going to drastically change compared to pure water. Like when we add strong acid or strong base to pure water, the pH either drastically decreases or drastically increases. But for a buffer, it won't do that. So what is a buffer made out of? So a buffer consists of a weak acid and its conjugate base, or a weak base and its conjugate acid. These two compounds must exist inside of the solution for it to be considered a buffer. It has to have a conjugate base and a conjugate acid pair. So how does this work? Well, when H plus is added to our buffer, so for example, we're adding a strong acid to our buffer solution, the conjugate base will react with the free protons being added, and it will remove them from the solution. So the effect of the strong acid will be mitigated by the fact that the conjugate base is going to be reacting and removing those free protons so that it won't be as acidic. Likewise, when hydroxides are added to a buffer, then the conjugate acid will react with the strong base by donating its free proton to the OH being added from the strong base to create water, and hence it will be removing free hydroxides from the solution so that it doesn't drastically increase the pH. So next, let's look at a conjugate acid-base pair. Let's look at an example. So we have acetic acid reacting with water, and this will create acetate and a hydronium ion. So acetic acid would be considered our weak acid, and acetate would be considered the conjugate base. We see that it's a conjugate acid-base pair because one of them is a protonated species and the other one is a deprotonated species. And for a buffer to exist, we must have both the weak acid, which is the acetic acid, and the conjugate base, acetate, in our solution. Let's look at another conjugate acid-base pair. This time, we will have the equation H2O plus NH3 reacts to create NH4 plus and OH minus. So our weak base would be ammonia, and the conjugate acid would be the ammonium ion. So we can see why we have to have these conjugate acid-base pairs exist in a buffer solution. Let's look at the top reaction. If we had added a strong acid to our solution, then this minus charge on the conjugate base would react with those free positive protons. And if we added OH, a hydroxide ion, into our buffer solution, then the weak acids would donate its free proton to the hydroxide and create water. And that's how it would mitigate the effects of a base. So you have to have a weak acid and a conjugate base, or a weak base and its conjugate acid, to have a buffer solution. So next, let's look at the Henderson Hasselbalch equation. So the beauty of the Henderson Hasselbalch equation is that it's able to correlate our pH, our pKa. It will also be able to correlate our conjugate acid concentration and our conjugate base concentration all together. And it's actually a simple rearrangement of the Ka expression. We know that the Ka expression from our weak acid base equilibrium video is H plus times the A minus concentration all over HA. So we're going to derive the Henderson Hasselbalch equation. What we have to do is we have to first divide H plus on both sides. We get Ka divided by H plus is then going to equal the concentration of A minus divided by HA. Next, let's do the log of both sides. So if we have the log of Ka over H plus is equal to the log of A minus over HA, we have this new equation. We can also expand our left-hand equation and write it as log of Ka minus the log of H plus is equal to the log of A minus over HA. If we bring log of Ka to the right-hand side, we can get the equation negative log of our H plus is equal to the negative log of our Ka plus the log of our A minus over HA. And what's the negative log of H plus and what's the negative log of Ka? Well, that's pH and pKa. So we get the final equation, pH is equal to pKa plus log A minus over HA. And this right here is our Henderson Hasselbalch equation for an acid. For a base, its pH is equal to pKa plus log B over BH plus. So it's pretty similar. We use pKa as well in our base equation, and we have to have the conjugate acid at the bottom and the base at the top, the weak base at the top. And we realize in both these equations, the protonated species is going to be at the denominator, and the deprotonated species in both the equations is going to be at the numerator. So these are the Henderson Hasselbalch equations that we will be using to answer our questions. Okay, so the first question is, calculate the pH after the addition of 0.05 moles of NaOH into a 1 liter flask of a buffer of 0.4 molar acetic acid and 0.4 molar sodium acetate. The pKa for acetic acid is 4.74. We're going to assume that the addition of NaOH to our flask is not going to change the volume. We can see that the question is essentially asking us, how is the pH affected when we add a strong base to our buffer solution? So let's start with the Rice table. The reaction that's going on is between a weak acid and our strong base. Remember, when we're adding a strong base to our buffer solution, the acid is going to react with the base. So we know our reaction has to be acetic acid plus NaOH, since it will be reacting with the strong base, and that will create sodium acetate and water. Everything's a 1-to-1 ratio, and we know that the initial amounts of acetic acid will be 0.400 moles. We know it's moles because we have the molarity given to us, and we know our volume is 1 liter. So to get the moles, it's simply the molarity times the volume, which is 0.4 times 1. Likewise, we know that we have 0.005 moles of NaOH that are being added, and we know that our flask initially also has 0.4 molar of sodium acetate, which will be again 0.400 moles of sodium acetate because we're in a 1 liter flask. Next, it's C, that stands for change. So what will happen? Well, we're going to be reacting with NaOH, and we're going to lose all of the NaOH in our flask since it's a strong base, and it will fully dissociate, and that will all react with the acetic acid. So we're going to be losing 0.005 moles of both NaOH and acetic acid, and we would be gaining that on our right hand side. We don't have to consider water because it's not going to affect our pH. So our final equilibrium would be 0.395 moles of acetic acid in our solution, 0 moles of NaOH left in our solution, and 0.405 moles of sodium acetate in our solution. So next we need to use our Henderson Hasselbalch equation to correlate all of the given data to get the final pH. So the pH is going to be equal to the pKa plus the log of the A minus over HA. It's important to realize here that our A minus to HA could either both be in the units molarity, or they could both be in the units moles. Since it's a ratio, the units will cancel out, but it's important to realize that they have to be both in the same units. So you can't have molarity on the top and moles at the bottom. You have to have molarity on the top and molarity on the bottom, or moles on the top and moles on the bottom. So in this situation, we can work with both moles, and we don't have to convert our final moles into molarity because the units will cancel out. So pH will equal 4.74. The pKa was given to us in our question. And the log of our A minus, and our A minus value would be our conjugate base, which is sodium acetate, and that's 0.405. And the value of our HA, which is our weak acid, is 0.395. And we get a final value of 4.75. So that is our pH after adding 0.005 moles of NaOH to our buffer solution. And does this make sense? Well, it makes sense because we can see here that the pH slightly increased, very little. There was a very little increase in our pH when we added a strong base. We could see the effect of the buffer. Usually if you added a strong base to pure water, the pH would drastically increase. But in this situation, it increased very slightly. All right, let's look at our next question. How many milliliters of 1.07 molar HClO4 should be added to 1 gram of imidazole? The molar mass is given to us to give us a pH of 6.99. The pKa of imidazole hydrochloride is 6.99. So it's important to realize here that imidazole is a base, and imidazole hydrochloride would be the conjugate acid. And what we're saying here is how many milliliters of our acid should be added to our solution to give us a pH of 6.99. So let's start off this question by looking at our reaction. I'm going to use general terms to make this question look a lot easier. So we have a base B, which we'll say is imidazole, and we're going to be adding acid coming from the HClO4. And we're going to be creating a conjugate acid. So we know from the Henderson Hasselbalch equation, pH is equal to pKa plus log B over BH plus. And our final pH is 6.99 because that's our goal. And our pKa given to us is also 6.99. So whatever our log of our B over BH plus must equal has to give us a pH of 6.99. Well, since our pKa is already 6.99, we know that our log of B over BH plus, this whole portion, has to equal 0, or else you can't get a pH of 6.99. So if log of B over BH plus is equal to 0, that means this fraction, B over BH plus, this ratio has to equal 1 because the log of 1 will be 0. So another way we can essentially ask our question is, how much acid should be added to the buffer solution to make a ratio of 1 to 1 B to BH plus. Because if this equals 1, then our log would be 0, and then our pH would equal our pKa. So to figure out how much acid we need to add to our buffer solution to get the ratio of B to BH plus to be 1, let's first calculate how much base do we have already. So it tells us we have 1 gram of imidazole, and it gives us the molar mass. So 1 gram times moles over grams, grams will cancel out. So 1 mole has 68.08 grams. So 1 divided by 68.08 would give us a value of 1.47 times 10 to the negative 2 moles of B. So we know that we have 1.47 times 10 to the negative 2 moles of imidazole, which is our base. So now that we know how much moles we have initially, let's use a rice table to figure out how many milliliters of acid we need to add. Our reaction would be B plus H plus, our base reacting with acid, to give us our conjugate acid. Our initial amounts. Well, we know our base is 1.47 times 10 to the negative 2. We know that we have to be adding some acid in our flask to make this reaction occur. And we know that we have 0 BH plus to begin with. And our change would mean we'd be losing that certain amount of acid to our base because it would be completely used up, and would be creating that same amount as our conjugate acid. So our equilibrium values is 1.47 times 10 to the negative 2 minus x. 0 acid is left because it's all been used up, and we have that x amount as our conjugate acid. So we can see our value of B is 1.47 times 10 to the negative 2 minus x, and our value of BH plus is going to be x. So now we have an algebraic way of setting up this problem. So the next step we need to do is solve for x. We need to figure out what that x value is, because that will tell us how many moles of acid was added. So 1.47 times 10 to the negative 2 minus x over x is the same thing as our B to our BH plus. And we know that this has to equal 1. So if I write the equation like this, 1.47 times 10 to the negative 2 minus x divided by x is equal to 1, we can now solve for x. So 1.47 times 10 to the negative 2 minus x will equal x if we multiply x on both sides. If we bring x over to the right hand side, we have 1.47 times 10 to the negative 2 is equal to 2x. And we get a final value of x is equal to 0.00734 moles. And again, what was x? Well, we said x was the amount of acid, or HClO4, that was added to our buffer solution. So we know this is how many moles we have to add to our solution. But the question is asking us how many milliliters of HClO4 must we add to our buffer solution. So we can't just stop here. We next have to convert our moles into a volume. So what do we have to do? The final thing we have to do is we have to divide our moles, which is 0.00734 moles of acid, by our given molarity of our acid. And our molarity is, again, moles per liter. So if we divide by molarity, we would have liters on top and 1.07 moles on the bottom. Again, this is the same thing as doing 0.00734 divided by 1.07 molarity. Both of these are giving us the same thing. And we would get a final value of 0.00686 liters. So that's the same thing as 6.86 milliliters. So the final volume of acid that should be added to our buffer solution to get a pH of 6.99 is 6.86 milliliters. All right, let's look at our next question. If you need to prepare a buffer of pH 4.3, which of the following systems would you use? We have a compound imidazole which has a pKa of 6.99, and we have a compound of benzoic acid that has a pKa of 4.19. So the compound we would want to use to make a buffer of pH 4.3 is benzoic acid. The reason we want to use benzoic acid is because it's much easier to get this pKa to that pH value. So if we use our equation pH is equal to pKa of plus log A minus over HA, it's much more easy to get a pKa that's 4.19 to a value of 4.3 than it is to change a pKa value of 6.99 to a value of 4.3. All right, so let's look at the last topic for today, and this is looking at buffers in biology. So our human body has its own buffer system because our blood pH has to remain close to 7.4, and any changes can be lethal. So we have a bicarbonate buffer system in our body. So what this means is we have H2CO3 in our blood, and it goes back and forth between HCO3 minus and eventually also CO3 2 minus. So our weak acid is bicarbonate, and we have the conjugate base as well. And so there's an equilibrium that's able to adjust with our pH in our system to make sure that we have a blood pH that remains close to 7.4. So if you enjoyed this video, make sure to subscribe, like, leave a comment, and have a good day.